All right, welcome everyone to 12.4. This is the cross product. As promised, right, there are two different ways to multiply vectors together that are really natural. They give you something that's very useful, and that's why they've stuck around so long. So we're going to be talking about the second one here. I need to define for you what on earth, again, is this thing, the cross product. And the claim is, as a part of this, we're going to have to review how to find determinants of 3 by 3 matrices. For those of you who had a great algebra class and remember, that's awesome, but I find that most students, this has kind of slipped. You know, especially we don't use them at all in Calculus 1 or Calculus 2, so in Calculus 3 we really need to bring back how do you figure out the determinants of these things. And then finally, we're going to use the cross product to hopefully find vectors that are perpendicular to two other vectors. And that is what it's used for, right? So this first goal, right, the thing that why we bring up this cross product, right? The goal is that if we're given two non-zero, non-parallel vectors, A and B, we want to be able to find a vector n that is perpendicular or orthogonal to both vector A and vector B. So that is the goal. That's what the cross product is used for. So let's go ahead and define this thing, and then I'll kind of make more sense of this here in a second, especially as we look at this example, right? So, okay, the cross product. We have two vectors, A, and it has components A1, A2, A3, and we have B with components B1, B2, B3. Then we can define we can define the cross product is given by the determinant. So it's the determinant of this 3 by 3 matrix. In the first row, we have these kind of standard unit vectors, I, J, and K. So these are vector I, vector J, vector K. And then here we have, well, A comes first, so I do A1, A2, A3, and then B comes. B1, B, that's a horrible B. One of the worst I've ever seen. There we go. B2, B3, closed matrix. Okay, so this is the determinant of this 3 by 3 matrix. So as promised, right, I'm hoping, well, I'm not hoping, but I think many of you may have forgotten, how to take the determinant of 3 by 3 matrices. So I'm hoping that this will be useful for you, right? So I'm going to be spending some time going over how do you figure out the determinant of a 3 by 3 matrix. Okay, so our goal, I'm going to show you kind of maybe two different ways here, is to be able to evaluate the cross product, right? So I have this cross, no longer a dot. So the cross between these vectors 1, 2, 3 and the vector -1, 1, 0. Okay, so if I was to set this up using this definition here, this would be equal to this determinant of the 3 by 3 matrix. And in the first row, we have the I, J, K. Again, these are standard unit vectors here. And then we'd have 1, 2, 3, that's my A, the thing that comes first in the cross product. And then the thing that comes second is -2, 1, 0. So I need to figure out the determinant of this matrix. And so the first way that I want to teach about determinants of matrices is my favorite way. It's the way that I'm always going to use in this class. Except for kind of, I'll show you the second way, just because, some people prefer this method, and that's completely fine. I won't be using it in the class, when I display problems, but if it works better for you, I want you to know about it. Okay, so the idea for figuring out the determinant of this matrix is that I'm going to work my way across this top row here. So the first thing is I, and I'm going to cross out the first row and the first column, because that's the one that I's in. So, okay, the first thing is I, and then I'm going to take the minor, right? So this is a smaller matrix right here, sometimes called a matrix minor, especially if you're looking up on, YouTube or Wikipedia or something like this, you may run across that term. So it's just a smaller matrix determined by, after you cross some stuff out. And I want to find the determinant of this matrix. And the way that you find the determinant of this matrix is you multiply the diagonals. And so you multiply this one first, 2 times 0, and then you subtract away 3 times 1. So 3 times 1. So it's always this diagonal subtract this diagonal. Okay. So, like I promised, we need to work our way across this top row. Let me see if I can successfully erase just the bits that I want to. So that was the first slot. Now, red. The second one. So again, I'm working my way I'm working my way across the top row. So cross out the top row, and I cross out now the second column. What's left over are these numbers right here, forming a different matrix minor. So in this case, I'm going to have J, that's the thing on the top here, and then its matrix minor is 1, 0, so 1 times 0, subtract away 3 times negative 2. Okay, and then finally, let's erase that, erase that, erase this. Oh no, I got my 1. The last one is K. There we go. And we cross out the first row, the third column, and what's left over? Well, K is the focus here, and then we have its matrix minor, which we're taking the determinant of. So it's 1 times 1 minus 2 times negative 2. Okay, and then the final thing here is that how do we combine these things, right? So now I have these 3 pieces. Let me go ahead and erase these red marks really quick. But we have these 3 pieces, and we want to know how do we combine these things. So the claim is it goes plus, minus, plus. Plus, minus, plus. So that's how we combine these things. And you can see that this is forming a vector in its own right. So this is some scalar right here times I. So let's go ahead. This is 0 minus 3. So this is negative 3 i's. And then let's see, we have 0 minus negative 6. So this is 0 plus 6. But we have this extra minus sign. So we have the 6, j. And then here we have 1 minus negative 4. So 1 plus 4 is going to be 5 k's. So this cross product outputs the vector negative 3, negative 6, 5. So based on the definition, I have now calculated out this cross product. Okay, so that's one way to figure out the determinants of matrices, of a 3 by 3 matrix, using what's called, this minor method here. So this is my favorite way. I'm going to be using this, and I'll talk about here in just a second why I'm going to be using this so much. But I'm going to go over this one more method that you can also use to calculate out this determinant. So let me go ahead and rewrite this one more time. 1, 2, 3, negative 2, 1, 0. And in this method, this one's kind of like a crisscross method. It's very interesting here. So the way that this method goes is that you repeat the first and the second column right next to the matrix. So I, 1, negative 2, j, 2, 1. Okay? And then what you do is that you take these, again, kind of a crisscross sort of deal, these diagonals right here, and these are all going to be counted positively. And then you take these diagonals right here, these are all going to be counted negatively. So I've maybe kind of ruined things a little bit. We'll see. Hopefully I can still read it. So, okay. I times 2 times 0. I times 2 times 0, that's going to be 0 i's. J times 3 times negative 2, that's going to be negative 6 j's. K times 1, that's going to be a single k, or 1k. Okay, and I guess, yeah, I could do 0 i's here. Now, along these diagonals, let's see, negative 4k is this one. And then here I have 3i. And then here I have 0j. Okay, so the ones that go in this forward direction, these are going to be all added together. The ones that are going in this negative direction, they're all going to be subtracted. And so let me go ahead and write in this next line here. So we have 0i minus 6j plus k, or 1k. And then I'm going to subtract away negative 4k. So that's going to be like plus 4k. And then subtract away 3i, and then subtract away 0j. And so if I combine all these like terms, right, 0i minus 3i, that's going to be negative 3i's. And let's see, negative 6j minus 0j, so that's going to be negative 6j. And then we have k plus 4 more k's, that's going to be 5k's. So altogether, this would be negative 3, negative 6, 5. And so we get the same result, right? The answer up here, well, should be the same as the answer down here, right? Otherwise, we made a mistake. The claim is this is 2 different ways to calculate out a determinant of a 3 by 3 matrix. So, again, you can use whatever method that you find the most useful or the most straightforward or whatever you like, right? I like this one the most because it is more expandable. The claim is if you go and you eventually want to take a determinant of a 4 by 4 matrix or a 5 by 5, right? Eventually you're doing maybe this thing linear algebra for like higher matrices, right? Not just a 3 by 3, but a 4 by 4 or a 5 by 5 or whatever, n by n matrix, right? The claim is this minor way actually extends that you can use this for higher matrices, for bigger determinants of higher matrices. So, and it doesn't work for this one right here. This is not an expandable method. You cannot use this later on. So I like this first one just because I have had to go through, right, you know, if you take especially like Math 314, 309, anything with a little bit of linear algebra, I mean, especially for engineers and stuff like this, kind of going through and actually knowing how to take determinants of any old matrix is very useful. So that's why I like, and I'm going to stick with, this first one. Okay, so this is the cross product. The claim is that it actually solves the question that we were out to solve, right? Originally, we wanted to try to find a vector n that was perpendicular to 2 specified vectors. So in this case, I went ahead and I graphed these things, right? We're trying to find a vector that's perpendicular, in this case, to the vector 1, 2, 3 and the vector -2, 1, 0. And so I've graphed these both starting from the origin here and going out, and you can see rotated, they're nice and in the 3-dimensional space. And again, our goal was to try to find a vector that was perpendicular or at a 90-degree angle to both of these vectors. And so here's our answer, right? Our answer was -3, -6, 5, and I can go ahead and graph that. You can see it's in red now. And it may be a little bit hard to see. Maybe we can rotate this around a little bit. But the idea is that this red vector is at a 90-degree angle for both of our vectors. So maybe here you can see it's at a 90-degree angle for that one. And here you can kind of see it's at a 90-degree angle for the other one. And so yeah, it's sometimes hard to see this. We can rotate it around, and maybe you believe me that this is actually at a 90-degree angle for both of these. The other thing we can do is sometimes graph the plane that contains both the blue vectors. So I went ahead, and we'll learn how to figure out this equation later on, but I graphed the plane that contains both of the blue vectors. And you can see that this red vector, this one that was supposed to be perpendicular, or a fancier word will be orthogonal, right, that this is actually perpendicular at a 90-degree angle to both of the blue vectors and the entire plane that it contains those blue vectors. So there's a really nice picture there. All right, so again, let's go ahead and formalize this in our theorem here. So in general, right, if we have these vectors A and B, then again, in general, if you take the cross product between those two vectors, that the result will be orthogonal, or aka perpendicular, to both vectors A and B. Even better yet is that we have a new way to kind of figure out angles between things, right? So if you take the cross product and you look at the magnitude here, the claim is this is equal to the magnitude of A times the magnitude of B times sine of the angle between them. So it's actually kind of friends. It's kind of a dual of the of the dot product, right? Remember when you take the dot product between two vectors, you have the magnitude of A, the magnitude of B times cosine of the angle between them. This one's sine of the angle between them. So it's somehow, right, they're friends. Okay, and then lastly, two vectors A and B are parallel if and only if the magnitude of the cross product is equal to 0. So remember, for dot product, if the dot product is equal to 0, then we have that they're perpendicular. If the cross product is equal to 0, or really the magnitude of the cross product is equal to 0, then they are parallel. Okay, so this is a theorem. It has proofs, right? This is nothing that you have to take my word for. I'm not going to go over the proofs in this video. They're kind of boring, right? But the idea is that, again, it is a theorem. You can prove these things. And so I want to go over at least the heart of the proofs, right? How could one prove these things? And so the claim is, right, if you take the dot product with either vector A or vector B, you'll see that both of them are 0. So the first one here is that this vector is orthogonal to both A and B. So the claim is, well, they're orthogonal or perpendicular if the dot product is equal to 0. So just go ahead and take A dot A cross B, and you'll see that that's equal to 0. And you can take B dot A cross B, and you will also get 0. So this just falls out. I mean, it's a lot of notation. If you thought the law of cosine's proof that I did for the dot product was bad, this is horrible. Much longer. Okay, the next one. For B, if you wanted to prove this, that the magnitude of the cross product is equal to the product of the magnitudes, magnitude of A, magnitude of B, times the sine of the angle between them. The claim is if you group this cleverly, you can get this. And so the dot product, is, of course, has some cosines in it, and of course 1 minus cosine squared is going to be sine squared. And that's where it falls out of. Again, this is just the heart of the proof. I'm not going to go through the full proof, but you can certainly find this online or in the book. And then finally, C, this is going to come directly from B, right? So if they're parallel, then the angle between them is either 0 or 180 degrees. So 0 or 180 degrees. If you plug that into sine, you get 0. So that falls out of B. Okay, let's try. Find a vector u that satisfies u dot 391 is equal to 0 and u dot negative 2, 4, 0 is equal to 0. So you're trying to find one vector that is perpendicular, right? The dot product is equal to 0. So you want a vector that's perpendicular to 391 and a vector that's perpendicular to negative 2, 4, 0. But that's exactly what the cross product does. This is kind of different phrasing to say, hey, take the cross product. The cross product has this property. So that's what we're going to do here. So I'm going to take the cross product between these two vectors, the two that we know. So I, J, K, 9, 3, 1, negative 2, 4, 0. Okay. And the way that I usually do this, I get a little bit faster here, right? So I write, this is the stuff that has the I's. This is the stuff that has the J's. This is the stuff that has the K's, right? Especially as you do lots of these things, right? We know that we're going to be working our way across the top row. We're going to do matrix minors things. And so we're going to have the I's, the J's, the K's, and I do the plus, minus, plus. Otherwise, I end up forgetting this minus sign. It's very annoying. I get the answer wrong too often. So, okay, make sure you remember this minus sign. That's a big thing. Okay, so if I cross off this first row and the first column, let me just do it in blue here. I'll have 3 times 0 is 0, minus 1 times 4 is 4. Okay, easy enough. Let's get rid of these. Come on, I believe in you. I don't want to get the 2 at all. Ah, dang it. I knew I was going to do this. All right, now if I cross off the J stuff, right? Okay, 9 times 0 is 0, minus 1 times negative 2 is negative 2. So it's like plus 2. Okay, again. See if I can do this. Oh, I'm horrible. All right, and then finally cross off the K stuff. And we have 9 times 4. That's going to be, 36. And then minus 3 times negative 2 is going to be negative 6. There we go. And if I want, I can go erase these. I made the lines a little bit longer now, so I wouldn't run into as much stuff. And so, okay, we have negative 4 I's. We have negative 2 J's, and we have 42 K's. Oops, I don't need that J. It's the second component. I already have that. So there we go. The claim is this is going to be orthogonal to both 931 and negative 240. But don't take my word on it. Let's check. So negative 4, negative 2, 42, and I want to dot 9, that's a horrible 9, erase, 9, 3, 1. So if I take that dot product, okay, negative 4 times 9 is going to be negative 36, negative 2 times 3 is going to be negative 6, and then 42 times 1 is going to be 42. Add those all together, do I get 0? Absolutely. Next one, -4, -2, 42, dot, -2, 4, 0. Okay, -4 times -2 is 8. -2 times +4 is -8. 42 times 0 is 0. So take the dot product. Is this equal to 0? Absolutely. So in this case, we've shown that this vector, -4, -2, 42, if you dot it with either one of these, you do get 0. And that's thanks again to what the cross product does. The cross product finds a vector that is perpendicular to both other vectors. All right. One last remark, this will be the last thing for the video, I promise, is that there's an interesting thing about the direction, right? So the direction of the cross product, if we have these two non-zero, non-parallel vectors A and B, then the direction of the cross product, A cross B, is determined again by the right-hand rule. I told you this would be coming up again, right? That is, the way your thumb points when your right-hand fingers curl through angle theta, first going A, then going B, right? So the order does matter here. The fact that this is A cross B means you do A first, then you do B. So, okay. In this case, you can see I pulled a picture out of the book, actually. So I have U's and V's is what they use in the book. I'm going to go ahead and switch this. Here's A and here's B. Here's A cross B, right? So you go first through A, then through B, and the claim is if you're using your right hand, your thumb points in the direction that this normal vector or orthogonal vector or perpendicular vector, right? So this points up in the direction of your thumb, right? So if you did B cross A, your thumb would be pointing in the other direction. And this is very interesting because it means that the order of multiplication actually matters in this case, which is very strange because usually it doesn't. But this is what we're going to bring up first thing in class next time here. So that's it for now. I've had a cliffhanger for you guys. I know you're very excited for class then. I'll see you shortly, and I'll spoil the rest of the surprise. Next time we'll talk about 12.5. The next video we'll talk about 12.5. I'll see you then. Thanks for watching.